new chapter, which is random variables. Not B. So random variables. So by definition, so if it's kind of from start to definition, so random variable say x is a function on outcomes of a random experiment with values in real numbers. So x is just a map, right, which sends, so all outcomes of the experiment, it's our probability space, so it's omega, and it sends it to real numbers. Right? So this is a definition, mathematical definition. So what's the meaning of this? So we have our old picture, so we have an experiment. And this experiment, so random experiment, so random, whatever it means, and it produces outcomes, right? So this is outcome omega, and it could be very complicated outcomes. So kind of you can, your experiment could be that you choose some individual and just ask many questions from these individuals. What is his income? What is his education or his or her education? So whether she or he smokes or not, and so many questions. So another experiment could be just kind of you kind of select the random text from the internet, and so it's also kind of pretty complicated thing. So if you want to study it, you better reduce something like complexity of the problem. And so this is where you get this map x of omega. So you calculate and you'll get some value of random variable. And so now it's old name, so random variable. So now in data science, that people would say that you calculate a feature of your observation. Right? So you have a very complicated observation. Again, so it may be kind of as complicated as a video on the YouTube. Right? And you calculate some particular feature of it. And so whether this video contains a nude image or not, kind of something like that. Right? So this is a basic picture, and so why kind of it's useful. Right? So the usefulness of this is just because it simplifies things. Right? So it's kind of, it simplifies things, so you don't need to take the whole complexity at once. And if you select the features wisely, it may give you more insight in the this random experiment. Okay? So you might be not very interested in everything about the outcome. You just need to be interested in some specific features of this thing. So if you want to understand the text, you are not really interested in every word kind of maybe of the text. And so you may be interested in some keywords or something like that. And so now this is a general picture. Second thing, so why we study it, because it's again, it's simpler, right? So rather than studying the arbitrary outcome, we now study the random things which are numbers. And the way to think about it, that we have something like a reduced experiment, right? So now we have you can think about that you have a random experiment which produces not outcomes omega, but the numbers x of omega. So it's a simplified or experiment. And so, right. So, but kind of you also need to kind of think about it that you can construct many features of the same on the same outcome. This is one of them, x of omega, but can be different ones. So it can be y of omega, can be z of omega. So you can kind of calculate many features of the same experiment. And so maybe example of this thing. And so example. So again, the examples may be too simple, but kind of. So you have a toss a fair coin, maybe a not fair, so just kind of a coin, a coin 2 times. Maybe even let us do toss not a coin, but maybe a fair die. So kind of 2 times. So now kind of the outcome of the experiment is not too complicated, but still kind of it's a pair of number. Outcome omega is a pair of numbers. So for example, you could have something like one outcome, the first outcome is a 5, another outcome is say 1. So it's a pair of numbers. Now you can have several random variables based on this outcome. So random variables, say the simplest one would be x1. It's the result of the first toss. X2, so result of the second toss. Second toss. Could be y equal to x1 plus x2. Right? So it's another kind of sum of the tosses. Could be something like say indicator, right? So you can also have something like indicator of the event that x1 is equal to x2. So it looks complicated, but that it means just it's equal to 1 if the first toss is the same as the second. The second maybe toss the same as the first. Это zero otherwise. And so these are all random variables which you can you can build more random variables, difference of x1, x2 kind of, but these are possible random variables which you can build on the just one experiment. And so this is just illustrate the idea of this thing. Right? Okay. So now, if it's if you can think about as every random variable as a reduced experiment, right? So kind of y is just kind of for every particular experiment with 2 tosses gives you a number, right? So it's kind of another experiment, a simplified version of the original experiment. So you can also define a probability mass function in this case, right? And so what is the probability mass function for the experiment? It's just a probability one specific outcome. Right? So if you apply this notion to the this reduced experiments, then you'll get the probability mass function of a random variable. So kind of nothing new, but it's kind of definition. So it kind of you should know what's the probability mass function of the random variables. So probability mass function of a random variable. So kind of I kind of will write RV kind of for shortness. Random variable x is a function. So it's a function and a function. So right, our random variable is a function on outcomes. The probability mass function is just is a function on the outcomes of this more simple random experiment. The function on, and our outcomes are real kind of on real numbers which gives the probability so real numbers x that x takes value x small. So what it means, so it's just kind of, so there is a special notation for this. So mostly kind of this definition is for notation, right? So we will write random variables with large numbers, right? So this is just kind of, and the values of this random variable with small numbers, right? So kind of large number is something like you can think about as a reduced experiment. So it's description of a feature, right? And small number is what is the value, it's particular outcome on this reduced experiment. What is particular value that this feature takes in this realization of the experiment. Right? So x, and we write it this way. So px, right? So if you want to specify everything completely, if you kind of, so px, so this is random variable, and of x small, so the value that it takes, it's equal to the probability that random variable x is equal to x. Now this is a little bit kind of not clear what it means, kind of that the random variable x is equal to x. So what's the event? So we'll need to measure the probability is a measure of the event. Right? So kind of it's kind of what about the original experiment? So probability was defined for original experiment. So kind of if you write in the full glory, then it will be probability of the set which consists of all outcomes such that x of omega is equal to this x small. Right? And so this is kind of completely kind of clear because this is kind of, this is a set. So here we have as a set of the outcomes of the original experiment. On all the sets we have a probability function. So, okay. Okay, so this is the definition of probability mass function, nothing especially new, kind of. So just kind of it's an application to this reduced experiment. So probability that the outcome in this reduced experiment is equal to x small. So here's an example. Let us look at our previous case. So two tosses of a die and maybe fair die. So we could calculate probabilities easily. Right? And our random variable x is equal to sum of the say call it tosses, maybe sum of the tosses. So if, for example, if omega is equal to 5,1, so first toss resulted in 5, second toss resulted in 1, then x of omega is equal to 6, right, to sum of them. Right? Also, kind of in full glory, you would need to write down the random variable in this way, x of omega, right? But usually, kind of people don't write omega, kind of, we just write x. It's you should understand that this is a function of outcomes, but it's a feature of experiment. Now, okay, so this is our example, and let us see what's the PMF in this specific example. Right? So what's the PMF of this random variable? Right? Now, if you look at this, so this random variable can take values which are only integers. Right? So kind of PMF on everything which is not integer is equal to 0. And now, if you ask a question, what's a p x of 1? Right? So the answer is 0 because it's kind of the smallest possible realization for each coin is 1. So 1 plus 1 is 2. Right? So it's not possible that you will ever get something smaller than 2. So it's equal to 0. So 1 is not possible. It is a sum of tosses. And so first time when it becomes possible, it's 2. So right, so px of 2, right, is equal to right. So you look at what's the possibilities. So in this case, the possibilities is the only possibility when this is realized is 1 1. Right? So the probability of this thing, right? So you can calculate it many ways, kind of. So one way is to see the total number of possibilities 36, right? So 6 for one die, 6 for another die. And so this is one possible outcome. So 1 over 36. So probability of this specific outcomes is equal to 1/36. And so, and this is the only possibility when the 2 is realized as a sum of two tosses. So this is equal to 1/36. Now you're looking at px of, say, 3. Right? So the next integer is 3. And you are saying, okay, so 3 is possible if omega is equal to 1, 2 or 2, 1. Right? So this is the only possibilities. Right? So now probability of every of them is equal to 1 divided by 36. So px of 3 is equal to 1 divided by 36 plus 1 divided by 36. Right? So it's equal to 2/36. Right? And you continue, right? So kind of it's maybe kind of in this case, it's easy to write down as a table, maybe kind of you write something like x here, possible values. And so here is p, this is random variable, px of x. So again, so the subscript is just to indicate what you're talking about, because if you have, instead of small x, you have a number, you kind of not really sure what's the random variable. Right? So now here you'll have a, okay, so what's the possibilities? Say we started with 1, after that was 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, right? So you cannot get more than 12. Okay, so now here you'll have a 0, here we have 1/36, here you have a 2/36. And well, kind of you can continue, right? So the 4 can be realized if you have a 3 possibilities, 1, 3, 2, 2, and 3, 1. Okay, so now, okay, so here will be 3/36 and so on. So 4/36. Now here's a 5/36. Here's 6/36 until you get to 8. Okay, so now if you have an 8, then the reasoning before breaks down, because, well, the reasoning before would be you start 1. It is possible, say, 1. For 7, it would be, for example, the possible outcomes are 1. So, for example, for 7, it will be the possible outcomes is 1, 6, then 2, 5, and so on. So 3, 4, 4, 3, 2, 5, and 6, 1. So you counted them, there was a 6 of them, and you got this 6 divided by 36. Now for 8, it's not possible, right? Because you cannot start with 1, 7. 7 is not possible, the outcome of the dam or of the die. So you'll need to start with 2, 6, right? And count how many of them, right? 2, 6, 3, 5, 4, 4, 5, 3, 6, 2, and that's it, because there are no 7, right? So you count them, it's 5 of them, right? 5 of 36, and you find a pattern. So right, you find a pattern again, it starts to decline. So 5, 46, 4, 36, 3, 36, 2, 36, and 1, 36, right? So the only possibility for 12. So this is again of kind of completely specified what's the probability mass function for this random variable. Okay, so this is it. Okay, so this is probability mass function for this specific random variable. Okay, so another example. Let us look at the probability mass function for indicator functions. Remember, kind of, so what's the kind of was an indicator function, right? So another example. Indicator function of an event, say A. Right? So now remember, the indicator function was defined in this way. So it was it's a function on the outcomes, right? And it was equal to 1 if omega was in the event, equal to 0 if omega was not in an event. So an example would be kind of, you get a kind of, so your outcomes is a photos from the web, kind of from internet search. And the indicator is a function which says that the photo event is the photo contains a dog, right? So you can see a dog in the photo, right? So indicator function would be equal to 1 if the photo contains the dog, this particular photo that you got, and it's equal to 0 if it doesn't contain the dog, right? So kind of it's 0, 1 function on the outcomes. And since it's a function on the outcomes, it's a random variable, right? It's a function of outcomes which gives you a real number, 0 or 1. So it's a random variable. Okay, so okay, so a random variable, it is a random variable. And so now if it's a random variable, we can ask the question, what's the PMF, probability mass function for this random variable? And so PMF of this random variable, and kind of I can write its indicator of A and forget about omega because it's kind of understood that this is a function. So this is our equation. So now to answer this question, we just need to think about what's the values, first of all, of this random variable. In this case, it's 0 and 1. So these are only possible random variables. So we'll need to have something like a table like that. So this will be X. Here will be P, indicator of A, so here's X small, and the values is 0 and 1. Right now, and here below we need to write down the probabilities that indicator is equal to 0 and 1. Okay, so for example, for 0, probability that, so the indicator function, PMF of indicator function evaluated at 0 is equal to the probability that the indicator function is equal to 0. Right? So, but when is the indicator function is equal to 0? It's only when omega belongs to the event. So it's equal to the probability that omega belongs to event. That's it, kind of. So this is a this is what should be here. So it's probability that that omega belongs to A. It's a probability of it's probability that it doesn't belong to A, right? So okay, and so this should be it should be equal to 1 minus probability that it belongs to A, so which is by definition probability of A. So it's 1 minus P of A, and it's similar, it's probability of A here. So you can write the probability mass function as a table, or you can write it usually kind of sometimes it's written this way. So it's kind of it's PIA of X is equal to 1 minus P of A. So probability, here's a probability. So this is a standard notation. P is standard notation probability mass function with small p. This is small p. This large p is a notation for the probability. 1 minus p if x is equal to 0. It's equal to p of a if x is equal to 1 and 0 in all other cases otherwise. So usually you can find the kind of the probability mass function will be written either as a table or kind of in this form. Right. Okay, so these are probability mass function. So now, so we started to study random variables because we said that it is simpler, right? So simpler than general kind of models. So now what's the simplicity? So what's kind of how we can see that it is simpler? So, and the first indication of that is that, so the outcome now, so the value of a random variable, so outcome in this simplified experiment and reduced experiment is just a number. And so for the numbers, you can compare two numbers. Which one is greater, which is smaller? There is an order on these numbers. You can add them together, right? And because of this, we have two concepts which we didn't have before. That's why kind of we started to talk about random variables and stop talking in general. Right? So these two concepts, one of them is a CDF of a random variable. And so what CDF means? So this is a cumulative distribution function. And we'll talk about it in a second, right? So this is one of them. And the second thing, the concept, it's expectation. So variable. Here is expectation of a random variable. And so these are two concepts which we didn't have before, which we could not kind of define in the general setting. One of them is because we don't have an operation less or equal on the general outcomes. We cannot compare the general outcomes. And we only can compare with numbers, so real numbers. And expectation is also not possible to define unless we can add things together. Expectation will be an average, something like an average. And calculate average, we'll need to be able to add together things. So now CDF at this moment will be not very important, right? So now right now we are studying, we study discrete random variables. which means they take finite or countable number of values. So remember, we talked about discrete probability spaces. And so discrete probability space was kind of that there is a finite or countable number of outcomes. And now we're talking about the discrete random variables. So this is a simplified experiment, and we also kind of have finite or countable number of values. So everything can be described by the probability of the specific outcomes. Right? So if you want to figure out what's the probability of n, you kind of just sum together the probability of each outcome inside the event. And it's enough. So probability of each outcome, right now, probability of each value of a random variable is given to you by PMF. So everything kind of explained by PMF. And so cumulative distribution function will be used later when we cannot do that. When we will talk about the situation when there is an uncountable number of outcomes, like the kind of the outcome is a real number. And we cannot really kind of the probability of each outcome will be equal to 0. So PMF will be exactly equal to 0 for every value of a random variable. And we'll still need to kind of to talk about them, kind of to describe them. This will be continuous random variable. For this kind of random variable, the cumulative distribution function will be indispensable. You will not be able kind of to do anything without cumulative distribution function. And so right now, kind of a cumulative distribution function looks like a curiosity, right? So kind of, but we'll still define it just to explain kind of that kind of this new concept, which you now can define and will not be able to define previously. And so the first thing, so right, so cumulative distribution function. So or CDF, right? So shortly CDF. So what is it? It's also a function. So definition. Okay, so CDF or small, okay, so large of a random variable x is another function, also function on the outcomes, on the values of a random variable. Right? So not the outcomes of the original experiment, but the values of a random variable is a function on, and the values are real numbers. Right? So it's a function on the real numbers defined also taking values in real numbers and defined as okay, so the special name for this is f. Right? So usually the usual standard name for the cumulative distribution function is f. Right? And it's f of x, also of x small. So subscript is just to distinguish what we're talking about, which random variable we're talking about. And it's equal to the probability of event that x large is smaller or equal than x small. Right? Okay, and again, so if you want to detail, so what this means. So it's a probability, so kind of rigorously, it's probability of the event which consists of all outcomes of the original experiment, all elements of the probability space omega, such that, okay, so there is no, it shouldn't be this one, such that this is column is for such that x of omega is smaller or equal than x. And so that's it. Right? So So now you can see that it was not possible to define before, because you need to say here is that the x of omega smaller than something. So in general, for outcome, you cannot say that the omega is smaller than some number, because omega is just kind of, can be kind of, I don't know, it can be a video kind of, so kind of something like that. Either a text, you cannot say that it's smaller than some number. You can say that it's equal to something, specific outcome, right? But you cannot say that it's smaller than some other outcome. Right? And so now it's something new, which is kind of you get here. And so let us look again on the example immediately. Right? Right? And so now example with the dice. Right? So two dices. So two dice. And before, so kind of, so usually you calculate CDF from, it's either given to you, right? So by the model, or you calculate it from the PMF. So just recall that the PMF of this thing was like that. So so you had a something like that. You had a X here. Here was a Px of X small, and you had something like a 0, 1, 2, 3, 4, so on. Okay, so 5, 6, 7, 8, 9, 10, 11, 12. And so these were outcomes. So these were values of a random variable. And you have here 0, 1 divided by 36. Now here there was a 2 divided by, sorry, no. Here was a, should start with 1. So here still 0. Here's 1 divided by 36. 2 divided by 36. 3 divided by 36. 4 divided by 36. 8, 5, 36. 6 divided by 36. 7 divided by 36, and so on, until here we'll have a 1 divided by 36, 2 divided by 36. So here's something. I could write it maybe kind of, it's not too many. 9 divided by 36 now. Yeah, so here's 5, right? So and it starts to decline. 5 divided by 36, 4 divided by 36, 3 divided by 36. Okay, so recover. So now let us see kind of, for example, what is f of x of say kind of 1, right? So kind of, so it's 1, right? So it's kind of probability that x smaller than equal than 1, it's equal to 0, right? So it's 0. Now what's f of x of 2? Right? It's again, so probability that x is smaller than equal than 2, and so it's here, it's 1 divided by 36. And f of x cumulative distribution function evaluated at 3. Okay, so now it's probability that x is smaller than equal than 3. It's equal, okay, so the only possibility that it's smaller than equal, and it's equal to 2, and it's equal to 3. Okay, so okay, so it's 136 plus 236. Right, and okay, so on, but say kind of, let us look at f of x of, say, maybe kind of, I say 3.5, right? So something like that. So, and I say, okay, so this is equal to the probability of x is smaller than equal than 3.5. All right, so it's still kind of 1 or 2. So it's still what? Sorry, it's still 2 and 3. Right? So there is nothing. 3.5 is not possible. 3.4 is not possible. Right? So it's still kind of p of x2 plus p of x equal to 3. It's still equal to this sum, and it's still equal to 336. So now, okay, maybe kind of what about kind of, so what about f of x of say 11? Right, in principle, what we'll need to do is to sum p x of 2 plus so on, plus px of 3 plus so on, plus px of 11. Right? So, okay, but this is a big summation. Right? And instead, what we can do is to say that this is equal to the probability, so that x is smaller than equal than 11. It's also, you can write it by the complementary rule as 1 minus probability that x is greater than 11. Right? And there is only one outcome which is greater than 11, which is 12. Right? So this is equal to 1 minus probability that x is equal to 12. So it's equal to 1 minus 1 divided by 36 is equal to 36. Okay, so what if f(x) of say 12? Okay, so you are summing all the probabilities, and the sum of all probabilities should gives you 1, right? So it's equal to 1. And so these are not so important calculations, just a kind of, so what's this calculation illustrate? That if you have a probability mass function, then you can calculate CDF by summing everything which is smaller, right? So in general, if you would like to write down a function, just kind of a formula, then you would write that f of x small is just equal to the sum of p of x of so here small, I need to change right as t, say, where the sum of all t smaller than equal than x. And maybe kind of I'll also write here that t is a value, possible value of x. And so why I kind of wrote it is just because, well, I want to sum which is not uncountable, not the sum of all possible t, right? Because it would be uncountable. I want to all possible values of x, right? Which is discrete in this case. Right. So now one thing is to look at this. So if we're talking about CDF, maybe kind of we should also draw a picture of what it looks like. Right? So now, okay, so maybe I'll need to go up here. And so kind of let us draw a picture of how it looks like. So here's f of x small, here's x small, and until 2 maybe kind of, yeah, so suppose I kind of use it. So here's a 2. So until 2, it's equal to 0, right? So before 2, this cumulative distribution function was equal to 0. So it went here. It was always equal to 0. Now at exactly at 2, it had a it was equal to 1 divided by 46. Right? So now here we have a jump. Right? So at this value at 2, when we approached it, we jumped to the 1 divided by 36. Right? After that, until okay, so let me kind of put here 3 here. Right? Until 3, we had the value of the cumulative distribution was equal to 1 divided by 36. So nothing changed. There was no new outcomes. When there was new possible values before 3. So okay, so cumulative distribution function went like that. Right? But at 3, there was another possibilities. Right? So at 3, we had that it was not only probability of x is equal to 2, not only this probability here, but also probability of x is equal to 3. We'll get a new possibilities. So we had a jump here. Right? So here's 2 divided by 36, new jump. Right? And okay, so this is kind of new value of a function. After that, it's kind of start again. So it was a kind of, it was a step function. It didn't change until we had 4. Okay, so at 4, it again jumped up. Right? Right? So, and the values to be became equal to 336. Right? And again, so after that, it's constant for some time, and it jumps again. Right? So at 5. Right? And you can see that it's still always increasing, right? It was not possible that it's decreased because it's always previous kind of values, some of the all previous values, but maybe kind of one more new value adds at some point. So it's always increasing, or at least it's not increasing, it's not decreasing, right? So it's constant at some interval. But at some moment it jumps. Right? So this is a feature of a discrete random variable. So it has steps, and it jumps at some discrete number of values. Right? Okay, so okay, so we see that cumulative distribution function is not decreasing. It's general, kind of. It's clear that it can be generalized to any example, and it's also it starts at 0, right? So it's 0 if you go sufficiently far to the left, right? And if you go sufficiently far to the right, well, it's kind of starts. If it's finite number of values, eventually it will become equal to 1. Right? So here it become equal to 1 at 12. Right? So if we have here 12, then, this is kind of distortion of the picture, but say something like here, so say 1. Right? So clearly it's distortion, right? So, but it's kind of at this point it becomes 1. So it's came here and makes a jump to 1, and after that, after 1 continuously after. So this is a picture of a typical cumulative distribution function. Right? Maybe kind of one more word about this before we go to the break. So this is kind of how we went from the probability mass function to the cumulative distribution function. So we kind of cumulated it, right? So cumulated the probability mass function. What about back? Kind of, can we go back from a cumulative distribution function to the probability mass function? And well, it's clear that if you look at, well, kind of, it's kind of you need to look at the sizes of the jumps. Okay? So if you look at what's the probability mass function of 4, okay? So you look at kind of before, kind of when the value 4 was not counted, the value of the cumulative distribution function was 2 divided by 36. By the way, I'm kind of probably making a mistake here, right? So you are not telling me. Okay, so kind of, so the value at 3 is not 236. Right? Right? So if you look at that here, right, this probability of x is equal to 2 plus probability x is equal to 3. So it's 136 plus 236. Okay, so this is a 336. Okay, so and the size of the jump here is equal to 236. It's exactly how much we added at this moment. Okay, so it's a probability of a free. Okay, so it's kind of when we went from 136 to 336, we added this value with p of x is equal to 3, which if you can look at here is kind of you read out that it's equal to 236. Okay, so now in same thing here. So here what we had here is actually 336. So this should be, it's kind of again, so this is clearly distorted, so it should be 636. Okay, so right, so when I kind of when I'm trying to kind of go back, right, so then what I want to read is how much it jumps at every of these things. So kind of right. So when I trying to figure out what's the p of x of 4, so probability mass function at 4. What I'm doing, I'm taking what's the cumulative distribution function at 4, and it's equal to here 636. Right, and I'm subtracting what it was just before. Right? So what it was just before, just on the left, kind of this 0.4. So well, if you want to write down it mathematically, we'll need to write something like just before, right? And the right thing is to write this probably as a limit. So it's a limit of when x goes to 4 from below. So I write it this one. So it goes to 4 from below of f of, so x small here, f of x small. And this is the general way how you can kind of calculate the value of the probability mass function if for the discrete random variable. For continuous random variable, the formula probably would be valid, but kind of not very useful because all the probability mass function will be equal to 0. But we will see it later. Okay, so here's generally. So look at here we have a general formula, this one, how to calculate cumulative distribution function from the probability mass function. So here's a backward formula. So p x of x small is equal to f of x small minus limit of t goes from below to x of x of t. Right, but it we don't need the formula, right? So to calculate, you just need to look at this picture of a table to be able to calculate this probability. So just to read it from the picture. Okay. All right, so maybe let's make a break for 5 minutes. So this was a long talk about PDF, PMF, and CDF, and after that we'll talk about something new. Okay. All right, so let me try to for for variety talk about next to the blackboard. So let me try to turn on the camera if it's possible. Okay. All right. So, okay, so we define the PMF and PDF of a random variable, and random variable was a simplification of a concept of experiment, right? So it's something like a specific feature of experiment or reduced experiment, but still kind of, you might be not satisfied with this and just wanted something even more kind of simpler, not only kind of just specific feature of experiment, which is still a random thing, right? Not even the PMF of this thing, so which is still a function, but something like a number. So we want to characterize the results of experiment by a number, and this is a kind of a if you need one number, then it's expected value of a random variable. And so, and the idea is that if you have a kind of two, so if you have a random variable x, which takes value x is equal to 0, and x equal to 100. So and and it represents something like, for example, a payment to you. And so there is a difference between the situation when the probability of 0 is equal to 1/2. So probability of 0 is equal, 100 is equal to 1/2. So it's one possible situation, and another possible situation is probability of 0 is equal to 99%, right? And probability of 100 is equal to 1%. Right? So this is a clear difference. It's kind of, if it's a payment to you, then this is much better than this is the payment to you. And sometimes you need to compare these two situations, right? So if you somehow more complicated than this, so something a payment which is complicated scheme, right? So which says, well, if this happens, then this would be paid. If this happens, then this would be paid. And so, and another scenario kind of, so, right? So you need to kind of compare between these scenarios, and which means that you need to reduce it to a number. Right? So, and the number is usually kind of something like an average, right? So in this case, you would calculate that the average is equal to 50, right? So 1/2 of 100, it's a 50, and here you would kind of calculate it. So this is 99%, but multiplied by 0, and just 1%, you'll need to multiply by 100. So you would get that we kind of here as well, kind of it's 1, right? So kind of the chance is 1%, and x is equal to 100, right? So you'll need to calculate the weighted average of the values, and the natural weight is a probability. Right? So it comes usually, these considerations comes from finance, kind of, right? And everything which is related to the payment. So by definition, so you can think as the expected value, so as a weighted average, it's intuitively kind of a weighted average of values of x, of random variable x with weights given by the probabilities of the values. Okay, so and kind of, so well, maybe kind of this is a long definition in words, right? So if we use our new concept PMF, then we can write it down as a formula, right? So the notation for expected value is E, right? E expected from E. Well, there are different definitions, very old, kind of in very old Russian literature and German literature, it was denoted by M, but so here is X, M for mean, I guess. So E of X, and so what is by definition? It's sum, right, over all possible values. Right? So, but I will not write all possible values because I just write over X. But it should be kind of, maybe I should write it kind of over. Okay, so I will not write. So all possible values of a random variable. And here's, okay, so it's average. So we'll need to write the x, right? And multiply by the weight. Right? Multiply by the weight, and the weight is the probability of this x. Right? So, and we already have a notation, it's PMF, right? So Px of x small. Right? So that's it, kind of. So this is a definition of the expected value. Yeah, so nothing very kind of complicated in here is very useful concept, right? So which is kind of possible because kind of you can add the values of a random variable. So because it's summation, so it's something like x is the outcome of it's a random thing, so it's outcome of a random experiment. But now you can add them, multiply by weights, add them together. So you cannot add two videos, maybe kind of in some sense, but you can if you kind of it's video contains something kind of it's if it's indicator function, so you can add the indicator functions, you can add features kind of usually. Okay. Yeah, so now our favorite example for this class, for this lecture, is the two dice. And x is the sum of the values. Values on this dice. Yeah, so we already know PMF. That's why kind of we use it, because we already kind of derived the PMF, so we can kind of calculate this thing. Yeah, so now, okay, so expectation of x is equal, and we start with whatever is possible. The first thing which was possible was 2 multiplied by the value from the PMF. So this was px of 2, right? And continue. So plus 3 multiplied by the PMF for 3. So this was, now I don't want to make the same mistake. So 2, right? So 236 plus 4 multiplied by 336 and so on, right? So now, okay, so maybe I will not write everything here, right? So maybe kind of the middle thing. So kind of what was the middle thing? 7 multiplied by 636 plus the next one was 8, and it was to 536, and again plus so on, plus so on. So don't forget this so on, right? And plus finally was a 12 multiplied by 136. Okay, so so you can calculate it kind of in general, but you can kind of use some tricks to calculate it. Right? So so the trick would be kind of to notice, for example, that 2 multiplied by 136 and 12 multiplied by 136 is equal to 14 multiplied by 136, right? Right, then 3 here and will be matched with 11 here, right? So kind of, and so on. So kind of, if you want to tricks, then you'll have something 14 multiplied by 136. It's just this thing plus this thing, right? And after that, this thing with another thing here with 11, it gives also 14, right? So you will sum 14, 136 plus 236 plus 336 plus 436 plus 536. But here I think that there is this trick doesn't work, because it's 7 divided by 7, and it's not matched with anything. Right? So plus 6 divided by 36 minus 7 multiplied by 6 divided by 36. Well, okay, so kind of you can calculate it with, but eventually you'll get some number. So if you do this, so you will get 7. So all right, so kind of just kind of let us write 7 and that's it. So kind of not calculated. Right? Don't do any trickery. So we'll get a 7. So it's there is an easier way to do it than doing this calculation. We will see it in kind of a little bit later. What's the simpler way to calculate the expectation of this random variable x? And so, but this is just an illustration. What's the expectation? Okay, so maybe kind of one other thing, kind of. So my kind of my favorite thing is kind of, let's look at the indicator, right? So function. So we skipped the cumulative distribution function. So haven't we counted 6 divided by 36 twice? Yeah, so yeah, we counted here, all right? So 7 by 36 twice, but I subtracted it, right? So that's why kind of I subtracted it. So if you want, so we can kind of finish it, kind of the calculation to make sure that we didn't make a mistake. So if you want to finish it, then kind of this is the sum of the arithmetic progression. Right? So from 1 to 6. I'm kind of afraid that we'll make a mistake. So kind of, so we will have here the 14, and the sum of the arithmetic progression from 1 to 6, you kind of have a formula. So you have a 7 multiplied by 7 divided by 2. Right? So this is a formula. And here you'll need to divide by 36. Right, and you need to subtract this 7, 6 divided by 36 minus 7 times 6 divided by 36, which kind of, I hope that it avoids double counting here. Right, so now what you'll get here. So here we'll get a okay, so here 7 times 7, so 14 divided by 2 is 7, 7 for 7, so it's 49 here, right, divided by 6. So 6 and 36 here cancel out, it'll get you 6 here. Okay, so 49 divided by 6, and here we'll have a minus 7 divided by 6. Right, so you'll have a here 42 divided by 6, so it's equal to 7. Okay, so, and the double counting avoided by, because I subtracted this thing here back. All right. We didn't count it most of them twice because we paired them. We not counted twice, we paired them. So we counted this with this one, and this one with something which is before. And kind of everything was kind of fine, except here, kind of we cannot pair it with anything. Right? So that's why kind of I needed to subtract. I paired it with itself, but I subtracted it back. Okay, all right. So, all right, so last example here is about the indicator function. Right? So what's the expected value of the indicator function? It's just kind of for practice, and it will be helpful for in the future to know what's the expected value of indicator function. Right? So indicator random variable. So just, okay, so again, so what's indicator? It's indicator of A of omega is equal to 1 if omega belongs to A. It's equal to 0 if omega doesn't belong to A. Right? Now we've figured out that the PMF of it is that P or IA of X. So PMF was a simple. It was equal to 1 minus P of A, probability of A, if X is equal to 0. Right? So at value of this random variable equal to 0, the probability is equal to 1 minus P, because probability that the kind of that omega is not in A. It's probability of the complement. And it was equal to probability of A if X was equal to 1, and 0 in every other case. Right? So now what's the expectation? And we just use this formula. Right? So just definition. Right? So, and by definition, we'll see that expectation of the indicator function of the event A, right? It's just equal by definition, so it's 0 multiplied by 1 minus probability of A plus another value is 1 multiply by the probability of A. So just definition, possible values 0 and 1 multiplied by their probabilities of these values. So 0 multiplied by anything gives you 0, and here's 1 multiplied, so it's equal to the probability of A. So now it's kind of, it turns out that it's trivial but useful. So probability of event is actually equal to expected value of indicator of this event, because it turns out that expected values are easier to calculate than simply the probabilities. So, all right, so let me see if we'll need to cover something else. Well, so one more example maybe. Kind of, so this is a more practical example. So one example, so actually example and a paradox, not sure if I have a time for paradox. Example. So suppose that you have a game, and in this game, it's so a game pays $1,000 if two dice okay, if sum of two dice is 2. Okay, so it gives you one on one die and one on another die, and minus $100 otherwise. Okay, so okay, so so what is the value of this game? Value of this game, and the value is kind of what's the amount of money that you want to pay for this game. Okay, so to be able to participate in this game. Now, kind of in this case, what's a game? Right? In this case, a game is a random variable. Right? So this is a payoff kind of. So you have some experiment which is kind of throwing the dice, and you have a payoff of this game which depends on this experiment. Right? So random variable is the payoff, right, in the game. And so it's exactly kind of, this is exactly kind of the description of this thing together. So this is the description of this random variable. Okay? So now what you want to figure out is the value of this game, and well, kind of typically in this case, the value of the game is assumed to be the expectation of this payoff. Okay? So what you will need to figure out, so let us call it x again, so maybe it should be called, so let us call it x and say what's the expectation of x. This will be our payoff, right? And so expectation of x, right? So two possible values, 1000 and minus 100. Right? So we say that it's equal to 100 multiplied by the probability, sorry, not 100, 1000 multiplied by the probability of this 1000. So it gives you 1000 if the sum of two dice is 2. So you recollect that this happens with probability 1 divided by 36. Right? So multiply by the 136. And plus, by our formula, second possible value minus 1000 multiplied by the probability that it's not 2. And this is kind of 1 minus 136. So it's 1 minus 1 divided by 36. Right? Now, kind of you calculate it, and all right, so kind of if you calculate it, then you'll figure out that this is equal to minus 69.44, something like that. Right? So the value of this game is negative. Right? So not only you don't want to pay anything for this game, you actually kind of want that somebody paid to you kind of before you agreed to participate in this game, because kind of the probability that you'll get, well, you have a large payoff in case you will have a 2, but it's so rare when they're kind of the minus 100 overwhelm this. Right? So kind of, so this is the thing that you need to consider. All right, so now I have on my plate one thing which is called Petersburg's paradox, which is also about games, right? So about thinking about these games, but maybe kind of let's postpone it to the next time. Right? So next time I will start with something confusing. All right, okay, so that's it for today. Today was a very important because we introduced the most probably important concept for this course: PMF, CDF, and expected value. And so next time we will talk more about the properties of this thing. All right. So if no question, then have a good weekend.
Thank you, Professor.
Thank you.
Thank you,
too.
Professor.
Thank you,
Thank you,
weekend.
Professor.
Thank you.
Have a nice weekend.